Alright, so what we are looking at today is continuity, and this is just an extension of a limit. Continuity just means exactly what it means. Is a function continuous? Do I keep going, or do I have to stop, pick up my pen, and draw again in somewhere else? So, first, it's more obvious to look at when's a function not continuous. So, in this first one here, we're going to say this is a not continuous function because I'm drawing here. Oops, I have to pick up my pen, come down here, and start drawing again. It's kind of like a little jump happening here. And we said this is the idea of the limit from the left not being the same as the limit from the right. This is like our two lovers are trying to meet and they're not going to the same spot, therefore their love cannot continue if they cannot meet. In this second one, we do have the limits being the same. We're going to the same spot. But at the same time, I have this hole here. So it's like our lovers are going, they're running to the same spot, but right here there's a big hole in the ground. Or this is like a river and there's no bridge. There's a big gap in between them. So even though the limit exists, there's no bridge. The function does not exist there. So again, their love cannot continue. And then this last one, same idea. Even though there is a bridge here, and they're approaching the exact same spot. It's like the lovers are going to the same spot, but the bridge isn't there, it's somewhere else. They didn't go to where the bridge should be. So this is where the limit exists and the function exists, but it's not the same. So to put it formally, what you need to have at a point, you need to have the function being defined, you need to have a limit existing, you need to be going to the same spot, and you need to have that limit being the same as the function. So you need to have the bridge, you need to have the limit, you need to have them going to the same spot, and more importantly, you need to have the limit being where the bridge is at the same time. So that's continuity at a point, and then we can say at an interval if it's just at every point over some interval. And we'll talk about what kind of functions already we know that are continuous pretty much everywhere. Alright, now types of discontinuity, we're going to call them either removable, down here, or non-removable. Non-removable just means like I have to jump. I have to pick up my pen to go to the other spot. Removables are where you have holes. It's like I literally just removed one piece, or I could remove the discontinuity just by filling in a hole. That's what it means to be removable. If it's a hole, it's removable. If it's like an asymptote or something where I jump, that's where it's non-removable. And that's what you're going to have to find are what kind of discontinuities we have. So here are the examples that we did. We want to say first, when do we have domain issues? That's where discontinuities will happen. Well, in a rational, it's whenever the denominator equals 0. So it's discontinuous when x equals 0. Now, how did we say before? How did I know if it was a hole or an asymptote? Well, in this case, no factors are canceling. That means that you said this was an asymptote, not a hole. Because it's an asymptote, we said this is a non-removable discontinuity. And that's what we're going to label it as, non-removable. For the second one here, I'm going to try to factor the top of x minus 1 times x plus 1 all over x minus 1. Where are my discontinuities? My discontinuities exist when x equals 1. That's my denominator equals 0. Now this is going to be a hole because the factor x minus 1 would cancel out. That makes this a removable discontinuity. Alright, number 3, piecewise functions will come into play a lot. Pretty much what's happening here, a little sketch of the graph, would be like we have some line going on like this, and then we have some parabola, maybe something like that. If this is continuous, these 2 points need to match up exactly. But it could be down here, it could be up here, or they could essentially meet. So what we need to do is at this breaking point, which occurs here when x equals 0 in this case, we need to check and see what is the function value from both sides. The limit from the left, the limit from the right. So all I do is just plug in 0. When I plug in 0, I should get 1. And when I plug in 0 here, I'm going to get 1. So I am approaching the same exact spot from both directions. Therefore, the limit exists. So, is there any break going on? No. We're going to say this function is continuous everywhere as a result. Continuous everywhere. And this last one down here, just to see what sine looks like. Sine we said was a periodic function, and it goes up and down like this. That's a very rough sketch, but it also is the same thing. It is also continuous everywhere. Sine and cosine are always continuous everywhere. All right, here's 4 more. I encourage you to pause the video and see if you can figure these ones out. Give it a try, see what you get. And here's a hint. On number 5, you actually have 2 types of discontinuity. All right, how'd you do? When you factored this first one, x plus 4 up top, and you should have x plus 4, x plus 2 on the bottom. You should have 2 different discontinuities. When x equals -2, x equals -4. The -4 canceled out. That meant it was a hole. That meant this was a removable discontinuity. The x plus 2, so x equals -2, did not cancel out. That means that one's non-removable. All right? In number 6, if I plug in this breakpoint of 0, I should get 3 here, and I should get 2 there. Well, those are not the same. That means that it is not continuous at this breakpoint in the piecewise function of x equals 0. And because of that, it's like a little jump here to get from 2 to 3. That makes this a non-removable discontinuity. In number 7, we know that this part here, x, is just a line. And we just showed in the other one that sine of x is a continuous wavy function. If I have 2 functions added together and each of them on their own are continuous, that means the whole thing itself is continuous. So this is a continuous function everywhere. No matter what we do, we have a continuous function. Now, last one, tangent. Is there any place tangent is not defined? Well, if you were to take a look at the graph, it would look kind of something like this. It just kind of keeps repeating in both directions. Each of these are little vertical asymptotes because if you remember at pi over 2, at 3 pi over 2, at 5 pi over 2 on your unit circle, you always got where you were dividing by 0. You have these asymptotes. So no, this is definitely not continuous everywhere. We have non-removable discontinuities at many places. At pi over 2, at 3 pi over 2, at 5 pi over 2, and pretty much just if we kept counting by a full pi, so 7 pi over 2, 9 pi over 2, and then going the opposite direction, just many, many different discontinuities. But mainly I want you to see these are non-removable discontinuities, and they happen over and over throughout the entire line.